In our last lesson, we learned, sort of in general, how to go about proving propositions or conjectures by using the method of mathematical induction. Math induction is not a proof method that works for everything. It's a very, very useful and very powerful tool, but it doesn't work for everything. And so over the next several lessons, we're going to go into a variety of other cases where induction can be helpful. And the next one that we're going to be getting into is sequences. So first we're going to review recursively defined sequences, and then we're going to explore how to prove the explicit formulas for their nth terms are valid. So before we get started, let's go and take a deep breath. And let's get into it. So hopefully you recalled that in the past, when we studied sequences, there were sort of two different kinds of sequences. There were explicitly defined sequences, and there were recursively defined sequences. Now, just in case you've forgotten those, I'm going to really briefly review the two of them. So explicitly defined sequences are ones where we know an explicit formula for the nth term. So for example, if I told you that a sequence was defined by this, it means that you can tell explicitly what the nth term is going to be in terms of n. So for instance here, if you wanted to know when n is 1, great, you would do u1 and you would just have to plug 1 in for n. So 3 times 1 minus 1 is 2. Yay! If you wanted to jump to the 10th term, no problem. You could find u10 because we have an explicitly defined function that says that it would be 3 times 10 minus 1, or 29. Okay, as another example, this one I decided to call a instead of u. A sub n is 2 to the nth power plus n. So if I wanted to know what the third term for this thing is, it's not a big deal. A3 is simply 2 to the third power plus 3. That's 11. Right? If I wanted to jump up to the 8th term, that's fine. We have an explicitly defined sort of formula here for what this term would be. It would be 2 to the 8th power, which is 256, plus 8, so that's 264. So explicitly defined sequences are ones where you are given an explicit statement for what the nth term is going to be. Okay? Now, recursively defined sequences, on the other hand, are ones where we know only how to obtain the next term in a sequence from the previous term or from a few previous terms. Okay, so as an example of this one, suppose that you know what the first term is. You know that the first term is 2, and then you're told this recursive relationship, that the n plus 1th term is simply double the nth term plus 1. Right? What this means is it means we can get the second term by doing 2 times the first term plus 1. Right? So in our case here, this would be 2 times 2 plus 1, which is 5. I can then easily get the third term by saying, well, it would be this 2 times the second term plus 1. You're basically always getting the next term in line by doing something to the term before it. So in this case here, this would be 2 times 5 plus 1, which gives us 11. Right? A very, very sort of famous or well-known example of a recursively defined sequence is the Fibonacci sequence, which is what we see here. Fibonacci sequence starts out with a first term of 0 and a second term of 1, and then it has this recursively defined relationship here that we can always get the term afterward by adding up the two terms previous to that one. My son heard the term recursively defined sequence and Fibonacci and came to the other room excited and smiling. So if I wanted to find out here what the third term was, I would add up the first term and the second term. And when I do that, I'd get 0 plus 1, which is 1. If I wanted the fourth term, the fourth term here is the second term plus the third term. So let's hear the second and third terms. The second term was 1, the third term was 1, and so this is 2. And we can continue this process on. This is what recursively defined sequences are. Recursively defined sequences are neat. There's a lot of applications for them. Lots of times we know how to build something off of previous things, but it is really nice to know what the explicitly defined version of it is. So now that we've sort of got this baseline for what explicitly defined sequences are and what recursively defined sequences are, we can move on and talk about how this even connects to mathematical induction. So the reality is recursively defined sequences are really helpful in a lot of contexts, but Often when we're working with them, we also wish that we also had an explicit formula for the nth term. It's not that explicit formulas are better than recursively defined sequences. They really are sort of like, pluses and minuses, strengths and weaknesses to the two of them. And so it's just nice to have access to both of them. Sometimes as we're inspecting the terms of a recursively defined sequence, we can sort of guess what the formula might be, but guessing isn't proving. And so mathematical induction can be used to actually prove that the guess or the conjecture or the proposition that we have is true. Now, just to point out, it's not like mathematical induction changes here. The 5 steps of mathematical induction are absolutely still going to be employed. You're still going to write your conjecture mathematically. After that, you're going to show that it holds for the base case, or sometimes base cases if you have a recursively defined sequence that has multiple starting values, like the Fibonacci sequence. You'll need to show for both of them. Your third step is still to state your inductive hypothesis, where we take the conjecture written mathematically and write it using K. Your fourth step is still the same. You're still going to write down your inductive step by letting n equal k plus 1, and then you need to show that that thing is true. It's still going to use what you did in step 3. Remember from our previous lesson that step 4 always uses step 3 in the process. And you're still going to end the math induction process by writing your conclusion and including that you use the principle of mathematical induction and using the values of n that it works for. So I'm really hopeful as we go through these next 2 examples that you're going to see that these problems feel really similar to the ones that we did in the previous lesson. It's just that some of the algebra changes and some of the details for how we actually show the work that mostly happens in step 4, that's going to be a little bit different. But the steps, the process is the same. So let's get into these examples. So in this first example, we have a sequence that's given by a recurrence relation. Right, here that is. And we're being asked to prove that the general formula for the sequence is right here. So remember that step 1 is that we're supposed to write mathematically what our proposition is, or the thing that we want to prove. Fortunately, that's already been done for us. So step 1 is provided for us by the problem. It's not uncommon that that's going to happen. If it's more of like a word problem, you may need to write it. But again, step 1 is done for us. Step 2 is our base case. And remember what we do in the base case. In the base case, we show that this works in the initial case. For this particular problem, my recurrence relation only requires 1 step, so I'm only going to need to show 1 base case. I'm basically going to do this for when n equals 1. Now, hopefully you recall when we did these problems yesterday, or in the previous lesson when we were working with series, we would do like a left-hand side equals right-hand side kind of thing. In this case, it's not so much going to be left-hand side versus right-hand side, but checking to make sure that what we get out of the first term from the recurrence relation is the same thing as what we get out of the sort of general formula, okay? So, we're given in the problem, we know that u1 is supposed to be 7, and so now we're also going to check, is u1 equal to 5 times 2 to the first power minus 3? So this is clearly 7 also, and so we write a quick statement like, hey, we've shown that the recurrence relation and the general formula both give the same value. I imagine that some of you may find it to be, I don't know that tedious is the right word, but frustrating to need to write these things so often. It's important to remember that proof is in a lot of ways mathematical communication, and so it's really important and really valuable that we're clear about it as we're working through it. It's also the reason that you don't have like 10 of these proofs as your assignment for the day. We generally only have a few of them. So let's go on to step 3, right? Step 1 was given to us in the problem. Step 2 is our base case. Step 3 is supposed to be our inductive hypothesis, right? So what do we do in the inductive hypothesis? Really, all we need to be doing is writing down, we're sort of assuming that my general formula or that my claim is going to be true for n equals k. All right, so when we do this, we're going to now assume, that u sub k, I'm just going back to my general statement, the proposition that I'm trying to prove, u sub k will be 5 times 2 to the k power minus 3. So this is the thing that I'm going to assume and that I'm definitely going to use as I go into step 4. Now remember what step 4 is. Step 4 is our inductive step, right? It's where we're going to write down the thing that we want to prove, and then we're going to prove it using what we just assumed in step 3. So I'm going to write it down. We want to show we want to show that u sub k plus 1, that the next term will be 5 times 2 to the k plus 1 minus 3. Right, this is the thing that I'm aiming to show. And remember, you're going to definitely use your inductive hypothesis, the thing from step 3, in step 4. Now, again, just like we did in the previous lesson, we're not really going to work with both sides of this thing. Instead, what we're going to do is we're going to work with the left side, right? And we're going to work on changing it into the right side. Now, remember from the beginning of the problem. From the beginning of the problem, we know our recurrence relation. We know that u sub n plus 1 is supposed to equal 2u sub n plus 3. I don't need to prove this. This is something that was given to me in the problem. This is the recurrence relation, right? So that means that, I could just use k instead. U sub k plus 1 is supposed to be 2u sub k plus 3. Now, if only we knew what u sub k was. Well, wait a minute. That's our inductive hypothesis, right? We assumed that this was going to work for the kth one, so I'm going to bring that in right here. U sub k plus 1 is supposed to be 2 times this relationship that we are assuming to be true. Oops, this is minus, not plus. Minus 3 plus 3. Okay? So I hope that what I did right there is clear. I went back and got my recurrence relation from the beginning of the problem. I wrote it in terms of k, and then I replaced the uk part, the kth term, with the explicit formula that I'm assuming to be true at this point. And my goal now is just to show that this thing is truly going to match what this says. Right? So when I sort of look at this thing structurally, I notice, this thing doesn't have a 2 on the out. Maybe I'll distribute this in and sort of see what happens. So when I do this, I get u sub k plus 1 equals 2 times 5 times 2 to the k minus 6 plus 3. Well, the minus 6 plus 3 on the end turns into minus 3, and that's good news because that matches the thing that's there. Matches the thing that's there. We're trying to show this one. This is a little bit different right here, though. Here I've got 2 times 5 times 2 to the k, and here I have 5 times 2 to the k plus 1. Do you see what's happening here? What's happening is that when I have 2 to the first times 2 to the k, I can combine those things. They have the same base, so I can add the powers. This is just going to be 5 times 2 to the k plus 1, and sure enough, that's exactly what we wanted to show. So now that I've effectively completed step 4, we move on to step 5. Remember that step 5 is our conclusion. I'd encourage you to pause the video and see if you remember the important parts of the conclusion and what you would need to write, and see if you can write it for this one. So remember, we want to include things like by the principle of mathematical induction, and, since we showed that it was true for the base case and for n equals k and n equals k plus 1, it's true for what values of n. So hopefully you're seeing that there's a lot of similarity between the way that we do mathematical induction on series and on these recursively defined sequences. We're going to see in all of our future lessons on mathematical induction that the process itself is the same. It's just a matter of what happens, particularly what happens in step 4, that changes a little bit to meet the demands of the thing that we're trying to prove. Let's go on and take a look at one more example now. In the second and final example, I want to get into another sort of difference that can come up when we're working with recursively defined sequences in mathematical induction. Sometimes with a recursively defined sequence, you'll have one that relies on 2 previous terms, or, in theory, even 3 or 4 previous terms, but we generally don't see them that require more than 2. And when that happens, we're going to have a little bit of extra work. First of all, your base case, you'd have to check not just that it works for the first term, but that it works for the first term and the second term. Because there's 2 of those things, we need to check that it works for both of those base cases. Second, your inductive hypothesis, which is step 3, has to assume that it works for both n equals k and n equals k plus 1. Again, because there's sort of like 2 steps in the recurrence relation, we need to make sure that our inductive hypothesis is going to cover both of those things. And finally, your inductive step 4, then has to prove that it works for n equals k plus 2, because, again, the recurrence relation is skipping across two terms, not just to the next one, and that is, again, still going to be based on your inductive hypothesis, which came from step 3. So you're going to find that this is, I think, a fairly natural thing that happens, but I wanted to make sure that we mentioned it and that we talked about it specifically. So the example that I have here is one of these recurrence relations where it starts with two pieces of information, both u1 equals 5 and u2 equals 13. And you can see in the recurrence relation that it covers two separate terms, right? We're going to be finding the n plus 2 term by relating it to the n plus 1 term and the nth term. Okay? And we're being asked here to prove that the general formula for this thing would be this, that the nth term would be 2 to the n plus 3 to the n. So step 1 is where we're supposed to write mathematically what our claim is. Has that already been done for us here? And if so, where specifically is the claim that we're going to be proving? Right? The claim that we're going to be proving is right here. This is our claim. And so this is basically our step 1, where that thing needed to be written mathematically. Yay, it's already written mathematically for us. So we're going to move directly on to step 2. And remember that step 2 is our base case. In this case, because it's a two-step relation, we need to show that it's true, show true, for n equals 1 and n equals 2. I need to show that it's going to work for both of these initial conditions that we're given. So what I'd like you guys to do, pause the video, make sure that you can see what you need to do in order to show that this is going to work for n equals 1 and for n equals 2. So what you should have done here is you should have done, well, the thing that I want to show is supposed to be that u1 is going to be 2 to the first power plus 3 to the first power. That's 5. And we were given in the problem that u1 was 5. So that one checks out. For u2, according to my formula, it would be 2 squared plus 3 squared. That's 4 plus 9, which is 13. And you'll notice we were given in the problem that the second term was supposed to be 13. So this one also works out. Remember, at the end of the base case, we want to write a short statement about how, like sort of what we've shown and where we are at the moment. I mixed up my language here just a little bit. Not mixed up in a bad way, but I just changed it up a little bit. What I did here is I showed that the formula we wanted to prove, this formula right up here, I showed that this formula works for n equals 1 and n equals 2, and that provides us a base case that's true. That's effectively what we need to do here. Now, remember that step 3 in the induction process, step 3 is where we make our inductive hypothesis. And in this case, because it's a two-step recurrence, I need to assume both that this is going to work for n equals k and for n equals k plus 1. And so remember, we're gonna take just a moment and write both of those things down, right? So we're gonna write down that u sub k is 2 to the k plus 3 to the k, and we're gonna write down that u to the k plus 1 equals 2 to the k plus 1 plus 3 to the k plus 1. And remember, we're definitely gonna use these things like, in important ways as we move into step 4, which is the inductive step. So in step 4, which is our inductive step, we want to prove it's true for n equals k plus 1. I'm sorry, n equals k plus 2, because remember we assumed that it was true for n equals k and n equals k plus 1. So I want to prove it's true for this, and remember I like to do that by sort of writing down the thing it is that we're going to be trying to prove. So we're going back to what this statement is, and the thing I'm trying to prove is I'm trying to prove that u sub k plus 2 is going to be equal to 2 to the k plus 2 plus 3 to the k plus 2 power. That's what I'm going to be trying to prove. Okay, so just like last time, I'm going to be starting with the left side, and I'm going to go back to the recurrence relation. Right? Remember at the beginning of the problem, we were told that u sub k plus 2 should be equal to 5 u sub k plus 1, 5u sub k plus 1, and then minus 6u sub k. Right, this was from our recurrence relation that we had at the beginning of the problem. And you can see what we have here is we have u sub k plus 1, which we have up here. And we also have u sub k, which we have up here. in our inductive hypothesis. So we're going to bring those two things down, and then we're going to remember that our goal is to get it to match this thing over here. So if you're feeling up to a bit of challenge, I'd say try this on your own, sort of give it a shot and see where you get. If you're concerned, maybe even try just taking one step, plug these things in, and see if you have any thoughts about what it is that you want to try and do. So let's see here. We know that u sub k plus 2 is going to be 5 times the k plus 1. That's the one over here. 2 to the k plus 1 plus 3 to the k plus 1. And then minus 6, and then times the u to the k, which is going to be 2 to the k plus 3 to the k. So I guess my thought is maybe I should just go ahead and distribute these things so that I can get everything, sort of see everything all at once. The thing I'm thinking about is I noticed that in this final version, all the 2's are together and all the 3's are together. So I'm kind of thinking that if we multiply these things out and then group the 2's and group the 3's together, maybe we'll be lucky and something will happen, right? That's what we're hoping. So u sub k plus 2 equals 5 times 2 to the k plus 1 plus 5 times 3 to the k plus 1 minus 6 times 2 to the k minus 6 times 3 to the k. All right, so then I said I was going to do some grouping here, so I'm going to bring these two together, and then I'm going to bring these two together. So u k plus 2 is, so I'm going to have 5 times 2 to the k plus 1 minus 6 times 2 to the k, and then I'll have 5 times 3 to the k plus 1 minus 6 times 3 to the k. So this is sort of what I've got here, right? My next thought is, okay, can I factor these? Is there any common factor between this and this? Well, yeah, both of those things have a factor of 2 to the k. So if I factor out that 2 to the k, what I'm left with in this first term is 5 and a single one of those 2's. And what I have left from this other term is minus 6. Okay, cool. We're good with that. Now, what about this other one over here? Is there anything that these two terms have in common? Both of these have a factor of 3 to the k. And if I factor that out, kind of like we had in the other one, there's going to be 5 and a single 3 left over, and then a minus 6 from here. Now when I go back through and simplify what's inside of those parentheses, this is 2 to the k times 10 minus 6 is 4, and then plus 3 to the k times 15 minus 6 is 9. And believe it or not, we're actually really, really close to what it is that we're going to be trying to show here, because remember, 4 is 2 squared, and 9 is 3 squared, and when I put these two things together, this is going to be 2 to the k plus 2, and this will be 3 to the k plus 2. And you'll notice that this right here is exactly what we were trying to show. Remember, at the end of our inductive hypothesis, it's valuable to sort of, recap what it is that you've done and what it is that you've shown before you go into the conclusion. So now step 5 is simply our conclusion. So step 5, conclusion. And remember, the conclusion is often very, very similar. In this case, we might need to mess with it a little bit just because our base case had a little bit more to it. But again, pause the video, take a moment to consider what you'd write for your conclusion, and then I'll share what I wrote here. So remember, in this case, our base case had to cover n equals 1 and n equals 2 because it was a two-step recurrence relation. So I wrote, we showed that the conjecture was true for n equals 1 and n equals 2 for our base case, and then showed it will be true for n equals k plus 1 if it's true for the two preceding terms. And so that means by the principle of mathematical induction, we've shown it's true for all integers n greater than or equal to 1. The more that we practice these problems, the more that we'll get used to the language and the vocabulary and the way that we structure these things. So I hope all that made sense. If you have questions, please make sure that you ask them, and best of luck as you work through the practice.